Welcome everyone. My name is Kai Cai. I'm very excited to start this course on linear feedback control. In this course, we'll explore one of the most powerful concepts in modern engineering and technology, the feedback control systems. Whether you notice them or not, these systems are at work all around you, keeping things safe, efficient, and comfortable in your daily life. This video is the starting point, an introduction to what the course is about and why it matters. By the end of this course, you will have gained 5 critical skills. First, you will learn how to model dynamic systems using state space representations. These are mathematical descriptions of how systems evolve over time. Second, you will be able to analyze key system properties, including stability, controllability, observability, and optimality. Third, you will design feedback controllers, both state feedback and output feedback, that can stabilize systems that may be inherently unstable. Fourth, you will develop feedback control methods for tracking desired references and to reject disturbances. And finally, you will code and simulate closed-loop systems, seeing your controller designs come alive in action. But why should you care about control systems to begin with? The impact is massive and touches every aspect of modern life. For safety, control systems prevent accidents in cars through anti-lock braking, keeping planes stable in turbulence, and maintaining safe operations in nuclear power plants. For efficiency, they save enormous amounts of energy in HVAC systems, optimizing manufacturing processes, and balancing power grids to prevent blackouts. Economically, we are talking about a $100 billion industry that enables automation across virtually every sector. And for quality of life, control systems are in your smartphone's camera stabilization, medical devices that keep patients alive, and home appliances that make daily tasks effortless. Let's start with something you can try right now, balancing a stick on your hand. This simple act demonstrates the core principles of control theory. Think about it. What are the key elements you need to successfully balance that stick? These are 2 fundamental components at work here. First, you have a system. In this case, the stick, which is an entity that changes dynamically over time. It's constantly falling due to gravity and responding to your hand's movement. Second, you are providing control. You are influencing the system's behavior in a desired way through 2 key actions: observing which direction the stick is falling or tilting, and acting by moving your hand to keep it balanced. Notice you observe the current state with your eyes, and then use your hand to drive the system toward your goal of keeping it upright. This is the essence of feedback control. Once you understand this principle, you will start to see control systems everywhere. In your home, your thermostat maintains temperature, your automatic garage door opens and closes smoothly, and smart appliances adjust their behavior based on your set conditions. In transportation, anti-lock braking systems prevent your wheels from locking up during hard braking. Cruise control maintains your desired speed on the highway, and modern cars can even park themselves automatically. Each of these systems observe current conditions and takes corrective actions, just like you're balancing that stick. In professional applications, the stakes get much higher. In industrial settings, robotic assembly lines must position parts with millimeter precision. Wind turbines automatically orient themselves for optimal power generation. And medical devices like insulin pumps deliver life-critical medications with perfect timing. In aerospace, spacecraft must maintain precise attitudes in the vacuum of space. Aircraft autopilots keep planes on course, and rocket landing systems perform seemingly impossible feats of precision. Here is one of the most dramatic examples of modern control systems, the SpaceX Falcon 9 rocket landing. This rocket uses real-time control to land on a tiny platform, enabling rocket reusability and save millions of dollars per launch. The precision required here is absolutely incredible. And here is what happens when control systems don't work perfectly. Early attempts at rocket landing often ended up like this one. This demonstrates just how challenging control problems like this can be and why we need rigorous methods and scientific approaches to solve them reliably. Now let's formalize these concepts with the building blocks of control systems. Every system has an internal state, which we will denote by X throughout. The state describes what the system is currently doing. For a car, this might be a position, speed, and steering angle. Next, we measure the output of the system, denoted by Y, which gives us information about some aspects of the system. This can be speedometer readings or GPS locations. We also have a reference, R, which represents what we want the system to do, like a desired speed or a target destination. But the system won't just automatically achieve all these targets or goals on its own. That's where we need a controller, and let's bring the controller into the picture. Like this, the controller generates input signal U to the system with the goal of driving the system toward the target. This configuration right now is what's called open loop control, in which controller has no access to the system's output Y, and thus has no way of knowing whether the system is actually going towards the target. And that's a serious limitation. This brings us to the last and the most important piece, feedback. The feedback allows the controller to compare the reference with the output, and then generate an input signal U accordingly. This input represents the control actions, like pressing the accelerator or turning the steering wheel. This point is so important. Let me repeat it. The key to the success of control systems is feedback. By using output information to shape the control input, we create a closed loop. That's why a feedback control system is also called a closed loop system. This feedback mechanism is conceptually simple. It leverages the difference between the reference and the output, what we call the error, to generate our control actions. Yet, feedback is incredibly powerful. It enables us to deal with three major challenges in practice. 1, uncertainty in how the system will behave. 2, disturbances from the environment. And 3, inherent instability in the system dynamics. Together, these are exactly the problems that make control so relevant. Let's see feedback in action. For the stick balancing, if we want the stick at 90 degrees, but it's currently at 89 degrees, say, our error is 1 degree. So the controller, in this case us, then decides how to move our hand to correct this error. For cruise control, if we want 60 kilometers per hour, but we are currently going at 65, say, our error is -5. Then the controller reduces the throttle to slow the car down. This continuous cycle of measuring, comparing, and correcting is what makes feedback control so effective. The applications are truly endless, from smart infrastructure to medical devices and environmental systems. The list goes on. Now, in this course, we will work systematically through 6 main topics. We'll begin with state models, the mathematical representations of dynamic systems. Then we will move on to the concept of stability and stability criteria, namely how to determine whether a system will behave in a stable way. Next, we'll study controllability and state feedback control design, making sure we can actually drive a system to the stable states that we want. After that comes observability and observer-based output feedback control. This is to deal with situations in which we can't directly measure everything inside the system. We'll then explore tracking and regulation using internal model control design to follow references and rejecting disturbances. And finally, we will tackle optimal control, designing controllers that minimize cost while maximize performance. Together, these 6 topics will give you a solid foundation in linear feedback control. The philosophy for this course is simple. The best controller is the one you understand. We'll take an intuition-first approach, building understanding before diving into complex mathematics. I will try to give you physical understanding by connecting abstract theory to real-world systems that you can visualize and relate to. We emphasize practical implementation, learning theory alongside hands-on coding and simulation. Success in this course comes from connecting mathematical tools to real-world problems that you care about solving. Whether you are interested in robotics, aerospace, manufacturing, or any field involving dynamic systems, this foundation will be essential. That's all for this introductory video. Thank you for watching and hope to see you in the next video.